So this is the actually one of the example we have already discussed in the previous lecture. And again, I am giving you this example again just to refresh your knowledge. And then I will start with the objective, actually, what is the issue behind this, the stability of the metal ions. And this is, you are observing these phenomena in your daily life, and you are going to apply in the experiments by using a lot of the metals and the metal science. And this is very, very important. Again, I am going to focus, this concept is very, very important to consider the stability of the metal ions or the stability of the water. So again, if this is the sorry. So this is the copper. Again, in similar to the copper, this is the example of the zinc. So if I simply ask, again, there are the two half cell of the waters, and one, this half cell should be considered at what electrode, at cathode or anode? What is your answer? So maybe you can just unmute for 1 or 2 minutes, then you can mute yourself. So I'm just engaging you to decide what we are going to discuss today. So this half cell, at what electrode we are going to consider this half cell, at anode or the cathode?
Sir, anode.
Very good. Another?
Anode.
Anode. So perfectly, this is the anode, because if any metal ion are going to react with the water, and water is on this form, it must has to oxidize. And if this is going to oxidize, it must be considered at the anode, and similarly it must be considered at the cathode. So this will remain, you can say this will remain the permanent option for you. This half cell should be at anode and this should be at the cathode. So be careful, because now we are moving towards the selective topic. We are not open to check again where is the what is the possible stability or the possible spontaneity of the chemical reactions. We are focused on the stability of the metal ions. So we are looking at towards the either direction is possible or not. So what would be your the answer? That means this you have to consider with this one, either this way is the spontaneous or not spontaneous. Zinc plus 2 is will react with water or not. What is the correct answer? Yes, please immediately, one of you
Sir, it
immediately
is the
answer.
non-spontaneous way.
Sir,
Very,
non-spontaneous.
very good, Shah. It is non-spontaneous, and what is the reason?
So it is because zinc has a lower reduction potential, and zinc is going to oxidize.
Very good. It's because at looking at the potential, the zinc is having the less potential as compared to the water. So this zinc may react with the oxygen, but this zinc ion is not going to react with the water, because in another way you can also calculate the cell. This is the right way for the calculation. So when this has to be oxidized, it must be at anode, and this should be at cathode by using this option. So you are using this option. So with this is cathode, this minus this, so your net answer would be in minus. That means this reaction will not occur. That means zinc plus 2 is stable in water. That's why when you prepare the zinc sulfate solution in water, it is stable in water. This is not going to react with the water. So the other option is the if I am considering this one, this has to be considered with this water. So either zinc will react with this water or not. Amna sir.
सर ये react करेगा इसके साथ.
Again, what is the answer? Again, this should be at cathode, this should be anode, because this is oxidizing, this is reducing. So that means this cathode, this minus and this minus will become plus, and you see this is the value, larger value, your net answer will be the minus. This is not going to react with the water. So maybe you can watch again and you can prepare your notes, and this would be the more interesting way to actually to pick up the idea over there. So that means both zinc and zinc ion are stable in water, and you can say water is also stable in the presence of zinc and zinc plus 2, because these are not going to react together. And the third one is the, does zinc plus 2 form the aqueous solution? Of course this will form the aqueous solution, because this is not going to react with the water. Now I am giving you another example, maybe because we have the shortage of time, and this you can solve yourself, and I will take your question. So this you can take this as an example and solve the stability of the bismuth plus 3 and bismuth plus 1. Again, you have to compare with this, and this you have to compare with this water. Calculate the cell potential. If it is positive, that means it is unstable. If it is negative, it is the stable. So uh, this is your exercise. So coming to the, now देर इज दी, बच्चे ये बंद कर दें, आप क्यों इसको डिस्टर्ब कर रहे हैं? So again, now if you want to predict the, I'm just focusing on first to explain you the objective of our today class. So there is the iron in the zero oxidation state, and of course again there is only the one option. Sorry. So one option for this one is to react with this water molecule, to react or to not react. This is, you have to decide. Again, in a similar way, you can decide. So your possible, now this is at anode and this would be at cathode. And this is a minus, and the minus from the
Sir,
formula. Yes, please.
screen sharing.
That okay. Thank you for reminding. Thank you. So this, if again I'm repeating, the question over here is again whether this iron is going to react with the water, and again your correct option will be this water, because these are two in the reduced form, these are not going to react together, and the correct option is this. And you have to find out whether is this a spontaneous way or the non-spontaneous way. If it is a spontaneous way, that means this is going to react with the water. And now you, how can you check the spontaneity? Just by calculating the cell potential. That means this is at cathode, this minus this. So this minus from the formula, this will become positive, and your net answer will be in minus. That means iron is not going to react with the water. So the question over here is how the rusting is happening. So rusting is the oxidation of the iron, and this is very common example. If you put the iron in water, and after certain time, there should be the oxidation, and this is the phenomena you are actually observing in your daily life. And but here this is going to tell you the iron is stable in water. So this is the main idea you have to pick up. This is the question, and I have to solve this one question, and in a similar way you can solve the other possibility of chemical reaction, whether this is happening or not happening. And the second option, this may be the another option. Let's suppose if I'm going to, this is the, okay, I have blocked. So Don't do this next time. So if iron, this is the iron, and again, if you consider the aerial oxidation and this iron, if you again calculate the cell potential, now this is the possible spontaneous reaction with this oxygen, because this is the higher potential, this will reduce and the iron will oxidize. So for the rusting, we have the two options. One is the aerial oxidation, that means to react with the oxygen, but hydrogens, there should also be the concentration of the hydrogen ion, and this is the possible way, and you can easily understand. But, and this is the option, this is also happening, but by looking at the potential, you can say that the cell potential is inactive and this reaction is the non-spontaneous reaction. So that means if this is the non-spontaneous, this iron is stable in water, or water is also stable in the presence of the iron. So that means if this is happening, there should not be the oxidation of the iron and there should not be the rusting of the iron. And this is the actually the against what you are learning right from your intermediate classes. Again, there is another question. All these are the question, and you may solve this in a similar way what we have explained before, stability of the iron or stability of the iron plus 2. Again, now this is the previous one was the oxidation of the iron to iron plus 3 state, and here this is the oxidation of the iron to iron plus 2 state. This is also being oxidized, and this may also help in the rusting of the iron. Again, there is the option either, if you have a water, of course you have to consider the spontaneity of this iron with the water, and the potential, again, this should be at the cathode and this should be at the anode if this is happening. And when you subtract this minus this, again your answer will be in minus. That means iron is not going to react with the water. And of course, if this is the option aerial oxidation, this is not our objective. Again, this is in addition, I am going to explain to you. This is going to be react with the aerial oxidation because this is the higher potential, this is the lower potential, iron oxidize and the oxygen is going to reduce. But here our concern is this: we are discussing the stability in water, not in the oxygen or with the other metal ions. So the first point is the water is important over here, and the other metal or the metal ion are important, by which we are going to discuss their stability. And again, if you want to react the iron with the water, your cell potential again will be minus. That means this iron is not going to convert it into iron plus 2 state even after the reaction with the this water molecule. That means iron is stable in the presence of the water. So again, there is a big question. If this is a stable, then where is the rusting of the iron? Why the iron is going to be rusted in the presence of the water? So the both case are the similar. Okay, you can see over here and you can calculate the cell potential. So I'm just keeping the pausing the recording. So now we are going to find out the way by which this iron is going to react with the water, and the water will reduce, or iron is going to oxidize either into plus 3 state or into the plus 2 state. So what are the way? So this is the actually the start of the today lecture. So if you look at the value of the all of these values, these are the standard redox potential values. So must remember, whatever the values written with the half cells, these are the standard half cell potential. Standard mean these are the at unit concentration of the metals ions or the unit concentration of the hydrogen, or if it is the oxygen, it should be 1 atmosphere, any ions should be 1 unit molar concentration. So then you have all these values. So the issue over here is actually this is prolonged to 1 or 2 lectures again to understand this one, and this is really very good to understand what is happening inside the water with the metal or the metal ions. So again, now one of the correct option over here is the change in the pH, because by using the different pH you can change the standard cell potential. Again, these are at the unit hydrogen ion concentration or the hydroxyl ion concentration, and when you change the pH, these hydrogen and hydroxyl ion are going to change. That means if I want to reduce this one, so what would be the possible answer? Answer is if this potential of this half cell of water is more than as compared to this 0.447, then of course this iron will react with the water, and this we are going to do right now. So how can we, this you cannot change, and there is only a possibility again in case of the cadmium of the copper. We have done the calculation by using the Nast equation. If you change the concentration of the metal ions, you will change the potential of the metal ions at these half cells. But here, I'm not going to change the concentration of the metal ions or the metal. I'm going to change the pH only. So if you change the hydrogen ions or hydroxyl ion, then these half cell potential are going to change. So look at the graph. This is the pH from 0 to 14, because we have the scale from pH to 14, and these are the two half cell. This is the first half cell of the water, and this is the actually this, and briefly it is written oxygen oblique water, or water oblique OH, or there is another half cell I'm going to explain later on. So this is the half cell of the water, which is going oxygen plus hydrogen ion forming the water. That means at anode half cell we are going to consider this half cell. So look at the value. When the potential is zero, then sorry, when the pH is zero, at pH zero, the value is 1.229. So this is the actually again 1.229, and maybe I will be using 1.23 just to round about this value. So that means if the pH is zero, that means pH zero mean hydrogen ion concentration would be unit concentration. When you take the log natural of hydrogen ion concentration, then it will be zero, because pH will be equal to minus log of hydrogen ion concentration. That means at pH zero, there is a unit concentration of the hydrogen ion, then the potential will be 1.229. And when you increase the pH, by increasing the pH, that means by decreasing the hydrogen ion concentration over here, then the potential is going to decrease. And how can you calculate this one? This is a very simple equation, and today if I have the time I will prove this one. And this is not the derivation, this is just the rearrangement. And for learning as a chemist, it doesn't matter you are learning physical, organic, inorganic, or the other chemistry, and we are just now playing with the Nast equation, and we come to the final equation over this one. And how can you plot this graph? This is the pH. Let's suppose this is zero. Then if you multiply with the zero, then only it will be the E is equal to E naught, and E naught is the 1.229. So at zero, the value is 1.229. And again, this is the standard cell potential. I am just putting the standard cell potential over here, because this is the E naught. Again, 0. This all becomes 0, and 1.23 or 1.229, that is written over here. So being a chemist, this is important to know. This is the straight line equation, y equal to mx plus c. That means this is the intercept, this is the uh, slope, and this is the x, and you are going to plot the cell potential on the y-axis and the pH on the x-axis. So this is the, it is starting. So this is From here to here, this is the intercept, and the intercept is the 1.229. It is, you are picking from here. So when you increase the pH, you can do at home, just multiply with 1, and 1.29 minus 0.0591, then you can get the value of which must be less than 1.23. Similarly, when it reaches at pH 7, then it is the, you can multiply 7 with this, and 1.23 minus this one, and this will give you the value of 0.816. So I have just mentioned over here the three values, and when you have the pH 14, 14 multiplied by this, and when you subtract solve this one, you will get the value of 0.403. So this is your the first half cell. Okay, so you can explain, you can just put the values of the pH and you can plot a graph. So this is the first line by using this half cell. In a similar way, this is your second half cell, which is at cathode, which we are going to discuss right now. So its potential is minus 0.8277, or maybe roundabout it is minus 0.828. So this is the equation, and I will again drive this equation, manipulate this one, and to come to the this final equation. And this equation is y equal to mx without intercept. This is with intercept. This is without intercept. Without intercept mean it is going to start with the 0, and let's suppose how it is come to the 0. If the pH 0, this all value becomes 0, so the cell potential will be the 0. So that's why the cell potential will be 0 over here. And then again, this is also the negative slope. This is going to decrease. You put the value of 7 over here, multiply this one. Now, because it is going to start from the 0, going towards with the minus sign, and the value is minus 0.414. And when you put the value of 14, this the value you will get, that is the minus 0.828. So look at the value over here. Actually, this value is at pH 14. That means, or you can say uh, pH 14 or POH would be 0. So because here is the OH ion concentration, and you can say when unit concentration of the OH ion, that means, and when you take the log natural of this one, POH will be equal to minus log of hydroxyl ion concentration. So with this unit concentration of OH, the pH would be 0. When pH would be 0, pH will be 14. So that's why the value would be here is the 0.828. So actually this is the graph. Again, I have only 5 minutes, so maybe I'm going to wind up right now over here this graph, and then I will again come to the objective and the question I have raised before about the oxidation of the iron in the presence of the water. So look at this value again. This, now this is the first line with the this half cell. This is the second line with this half cell, and all pH range from 0 to 12 is covered. So that means this is actually pH 4 to pH 9 is the pH of the natural water. It may start with the 4 to 9, but ideally it is having the 7 pH. We going to consider the pH of the sign 7, but it may be plus minus. It depends on the pH of the water. Some areas we have the more hydrogen ion and some have the less hydrogen ion. And this is the actually the area highlighted over here in between 4 to 9, or you can cover up the whole area. This is whole area inside the this line. This is called the stability of the water, and that means the water is stable inside of this graph, or you can say all the metal ions or the metals whose potential are going to exist within these regions are also stable. So this is the big statement, because it may be difficulty right now to understand. Later on, I'm one by one I am going to explain. But important over here is to remember how all the metal ions are going to stable inside, And if they are having the higher oxidation state, that means over here or over here lower oxidation state as compared to the this half cell, then these are the unstable. That means metal and metal ion are also unstable, and the water will also be unstable. So this graph is generally the stability of the water. Inside, the water is stable metal and the metal ions are the stable. Outside this boundary, the water is also unstable and the metal or the metal ion are also unstable. And how can you plot? This is the way, by using this equation you can plot this graph. So again, the question remain unsolved. I have limited time. I want to explain one of the equation right now because we have again the 15 minutes. So better to be with me. I'm going to end this video. So please rejoin me again.